Okay, so good morning. So we continue our study of the quantum mechanics of, or rather statistical mechanics of quantum ideal gases. And I'll just conclude the Bose-Einstein condensation with some comments. Okay, so so the first comment is that the is about the sizes and numbers of atoms, number of atoms rather, in BEC, which we have seen in experiments. So it's usually the ones which are used are alkali metals, so rubidium, sodium, lithium. Okay, so the first BEC had only around 2000 rubidium atoms. Okay, but later numbers went up to 10 power 7. Okay, and probably even more. Okay, I don't know the exact number, but this is at least something which I looked. But this report was slightly old, so obviously they've gotten better at doing these things. So, and the second statement I said is that there was a two-step cooling involved. Right? So there was a okay, the first one is laser cooling. First step. And the second thing, which I told you, is which you switch off. Basically, I mean, that's a very crude way of saying something slightly more sophisticated, but it's called evaporative cooling. So you let the faster guys evaporate, and whatever remains will have clearly lower energy. And hence, if they thermalize, they'll have lower temperature. Okay, so it's called evaporating. Okay, and the temperatures go up to, I guess, microkelvin here. I don't know here. This is probably millikelvin. Okay. So I request you to check these. Numbers are important, and so understand these things. And the third thing is that the 2001 Nobel Prize was awarded for experimental I shouldn't call it experimental, for actually creating BEC condensates. Do people know the names? Cornell, Wieman, and one more. Kettle, I guess. Yeah. Okay. So, like I said, you look up the literature on these things. And last thing is that so we observed or we showed theoretically rather BEC happen for ideal bosonic. Okay, but in real life, and everything is an idealization, and so the question is, what do interactions do? Okay, Do they preserve the fact that BEC happen, or they will change the critical temperature, etc., etc.? Okay. So, so this is, I think, I don't know how well, I have no idea how well this has been studied. Okay. So, exercise actually, do literature survey. Okay. So, so in other words, what I'm trying to get at is, will real gases also show Bose-Einstein condensation? Okay. So experimentally, we know that if you have a gas of rubidium atoms, or if you have a gas of sodium atoms, they will form a condensate. But how general is this phenomenon? We don't know. Okay. I don't know at least. Okay. So I'll pause here. Are there any questions and comments about BEC? Okay. So yesterday, I remember when I wrote the formula for the free energy, I said there's a log mu. I don't know how it comes. It's actually very simple. It's not nothing deep was coming in. The minute I started writing it, I could see where it came. Okay. Anyway. Okay. So today we will move on to ideal Fermi gases. Okay. And these have qualitatively very different behavior from Bose gases. And but of course, we obtained formulae for we computed when we computed the grand canonical grand potential, we did it for both. We just put it was only a signs here and there, right? We obtained a formula for the grand potential. Okay, for a gas of fermions. Okay, and so again we can write formulae similar to what we wrote. So yesterday we wrote something like so P upon kBT. The PV upon kBT will be log Q, if you remember. So if you just write that out, this would be uh, P by kBT. So let me just write that. And write it in a very simple form so that it's just P by, it's just 1 by lambda cubed. And similarly, okay, so these are identical to the bosonic integrals except for the sign. So where? Okay. And so if you remember, we considered these integrals. So these integrals were discussed in problem set 10, right? Okay. In particular, we showed that, f5 by 2 of z has an integral in terms of with an integrand which is a log. That's what you get naturally. You don't get what I wrote, but integration. Okay, but we showed that by integrating by parts, it's equivalent to whatever we get. So this was identical to these things. So basically, these formulae are, basically the same, similar to what we had for. Okay, similar to what we had for the bosonic case, except we get this different function f of z. And now the question so now we can ask how does one determine the chemical potential? Okay, so how does one which formula will we use to do that? In the box there are two formulae. Which one should I use? What are the macroscopic properties we will know of the Fermi gas? We'll know the number, we'll know the volume, so we'll know 1 by V. Okay, so we should use, and lambda is the thermal wavelength, so it depends only on the mass of the thing and the temperature, right? So you should just think in terms of, so the first one isn't, it's the equation of state, right? So this is the equation of state. Okay, so we'll use the second equation, which we can rewrite as lambda cubed upon V equal to F 3 by 2 of Z. Okay, so the thing is that we remember that there is a f3 by 2 of z as a representation in terms of this is what we get. Okay, and so yeah, so now what was the argument? So now I want to so what is the argument? Actually, I made it myself, but now I that says that z belongs to 0 to infinity, right? And why is that? Yeah, because the point here is that if you look here, this is an equation which gives you pressure in terms of all the other quantities. So pressure is so the variables in your grand canonical ensemble are chemical potential, temperature, volume. I mean, you look at your variables, not even number of particles. Okay, or if it's canonical ensemble, number of particles. So, but if you think canonical ensemble, what you want, so basically you want a relationship between number density and mu, and that's what the second equation is. Okay, the first equation has, if you wish, two unknowns, p and okay. So there is what is the argument? Anybody? Okay. No, more like I'm not worried about 0. Z is e power beta mu. So mu is another way of saying it is mu. So what one is saying here is that Z can take values greater than 1. Okay, mu can be. Okay. So that's what I'm asking. So 0 to 1, I mean 0 is not the problem. Why is it? I mean it can exceed 1. Okay. Anybody? Hmm? Yeah. That's what we, yeah. So, yeah. Hmm. Yeah, I mean, it's tautological what you're saying. I'm asking why that is. I mean, what you're saying, that's what my question is. Why is that? Yeah. Okay. Hmm. So, yeah, so let's look at this. So you're saying something like this in this integral. So anyway, go back, play with this integral. And the point is mu can be positive. Okay. So unlike for bosons, it can never, I mean, so that is one point. And then for what about what do we expect at high temperatures? High temperatures, low densities, number densities. What do we expect for say ideal Fermi gas? What is it we should expect? So no, it's actually much more simpler. Any even an ideal Bose gas or even an ideal Fermi gas, when it's in the dilute or the high enough temperatures, we'll discover that you can it'll approach the answer for an ideal gas, right? The chemical potential of both Bose and Fermi gases should approach that of an ideal gas. Now the question is, what is the sign of the chemical potential for the ideal gas? Anybody remember? Okay. Okay. So this is what happens, and but it's a very easy way to see why mu should be positive at low temperatures. Okay, so Fermi gases, but let's come back to this equation, which is this is the equation that we need to solve, and let's ask. So it is determined by this quantity lambda cubed by v. So let's rewrite what it all the terms it contains. So v is just capital N by v. Lambda is h cubed divided by 2 pi m kbt power 3 half. Okay. So what is happening out here? So for so high temperatures or small number densities, this lambda cube by v is small. So it's dimensionless, so it's less than 1. Right? Many ways to see this. As T becomes larger, this thermal wavelength becomes smaller. And as number density becomes lower, this term will become smaller. So any combinations of these guys will be fine. And the left-hand side is a dimensionless quantity. This is lambda is a length. Length cubed is like volume. This is also. Yeah. So this is dimensionless. Okay. So lambda cubed by this thing will be less than 1. Okay. This is just worth knowing. So then we can, so can we go back and see this point that will it be negative? If so, what is the answer? Okay. And does it agree with what we did? So what we can do is look at this formula again. So this is a small, this thing. So another fact is easy to see again is that fn of z is a monotonically increasing function. Okay. And so so when lambda cubed by v is less than 1, we also expect z to be small. Okay. So then we can approximate fn of z. Okay. By is the sign correct here? Is it minus? So for L equal to 1, oh yeah, it's fine. Okay, so f in particular f3 by 2 of z will be equal to, the first term will be z by 1 power 3 half, so it will just go as z plus corrections. Okay, that is order z square. So for small z we can use this formula. So for small z, we get z equal to okay, and you can go back and check. Okay. So if z, so you can see that lambda cubed by v I said is less than 1, actually probably much less than 1. So you can see that z also is less than 1, which implies mu is negative. Okay, and this is the answer from matches the ideal gas value. Okay, so this is one feature which we can see. But now let's just look at but if you want to get a more accurate, if you want to see corrections to ideal gas behavior, what is it we have to do? We have to use the fact that lambda cubed by v equal to, first term is z and the second one is minus z power 2 power 3 by z square by 2 power 3 by 2. Okay. Plus, of course, there are other terms. So now this is a quadratic equation. You can invert it. You can invert this. I'll just copy the answer, but exercise to show this. Okay. So this is what we get for z. Okay. So once we get the value for z, we can go back and we can look at the equation of state now. P by kBt, which is the first one. Okay. So my idea here is I want to get the first correction to the ideal gas equation state. So PV by kBt and kBt is 1 plus something, right? The virial expansion. So we already have the thing for exact thing. So I've just written the first correction to Z, and if I put that into the formula, then I should see the corrections which come. Okay. So what is the first correction? By the way, we can do the same thing for even the Bose gas. So exercise is do the virial expansion for the Bose gas. Same thing. Okay. It's just the formula will be, instead of doing F3 half, you will do G3 half. Okay. So let's look at the equation. It is PV by kVt. Okay, which we can multiply and write it as V by okay, and so again F5 of half of Z, what is that? It's equal to Z minus Z square by 2 power 5 by 2, right? Okay, so what we have to do is, now we have Z to this quantity. Don't worry about V by lambda cube, that's large, but the Z is already of that order, so it will bring it down. Okay, so you can simplify this and you will get this is equal to, okay, so again I'll just write the answer. Some power of 2 some 2 power something times so I think it's 5 by 2, but okay, so in general this will have the following structure. Okay, and if you compare these two, we get as the second virial coefficient A2 is 1 by, and if memory serves me right, if you do the same thing for the Bose gas, you'll get A2. I think numerically it's the same answer, but there's a sign difference. A2 is minus of that. Okay, but I won't swear that that is the answer. Okay, so yes, but you can see here, you can go ahead. Exercise is compute A3. Okay, you still need to complete the calculation here by keeping terms. So if you want to do A3 now, you'll need to go here and get Z to one more order, step 1, which you can recursively, you can do that, and then or you just put in an ansatz that Z equal to some constant. So it's just this lambda cube by V is the small parameter in which it's being expanded. So you write it as a power series and plug it into the previous thing and then match coefficients to order by order. You will get it. Okay, so that's another way of recursively doing that. Okay, so you also compute A3. So this is a fun exercise. So now, so I'll pause here for some questions. So what we have done is looked at the high temperature, low density limit, but we did little better. We asked how does it deviate from ideal gas behavior, and we can see. So the first, second virial coefficient is a deviation. We also saw we computed the virial coefficient in a different example. Does anybody remember? Deviations from ideal gas law. Where did we see it? Before quantum gases. Van der Waals gas or real gases. Okay. Right? So we got a coefficient. We had a particular expansion there in terms of the potential. What was the data which went into? So there's an exclusion volume, and what was the other thing? One more parameter. Right? Anyway, in terms of the parameters in the Van der Waals gas, the two parameters they showed up in the first virial coefficient. Okay. So now we will do the more fun case. So okay. But now, what does this mean? It means lambda cubed by V is now greater than 1, or may possibly even much greater than 1. Okay. So now, so question is, how does one determine? Now determining, so how does, okay. So now, since this is large, we know that Z has to be large. It has to be greater than 1. Okay. And if you make this really, really large, or if you go to very, very low temperatures, you know that Z can be arbitrarily large. And so the thing is that we can, so we need a different expansion. Okay. So to determine, see this formula which I wrote, this expansion, not this. This holds for mod Z less than 1. Okay, you might say, why did you put a mod? I mean, I'm thinking in terms of complex numbers. As an expression, we can always do that. You can think of Z as being complex. And so this is true only for small arguments. For large arguments, okay, so we need expressions for large arguments. Okay. And so there is a way of getting it starting from the integral. We have other representation, right, in terms of an integral, which is rather different from this thing. So you can use that and use methods from that. So I'm not going to do that. I'll just copy some formula, but one can derive it. Okay. So in fact, this book which I'm using, which is Kirsten Wong, she has actually given the derivation for F 3/2. Okay. Three by 2. Okay, so this is what you get. It's quite different. There's no reason for it to. Okay, so now what is it we have to do is we need to, so if we need to solve, so what is it we have to solve? We have to, so we could truncate, for instance, let's say we'll keep the first two terms, or We could do it recursively. First do only log z 3 by 2 equal to that, and then do a power series. We need to, you know, use this to determine log z and maybe then z and or b. Okay. So again, this is an exercise, so which you can do. I don't expect you to derive this formula which I just wrote. Okay, so I mean, there's no shame in looking it up, but at some point you should derive it on your own and see, because these methods which you use are used again and again. Okay, so it's kind of fun. At least I think it's a fun exercise. Okay, so but once we have this, so we can we can truncate some equations. Say lambda cube by v is equal to 4 by actually I can even pull this. Let it be. So you need to keep track of orders of things. Okay, so once you do this thing, you will get an expression. So I'll write the formula, which exercise. Okay, show that. So, but remember, log z is e power beta mu, so log z is beta times mu. So up to a factor of beta, it's mu. Okay, so exercise show that mu equal to some quantity which I'll call epsilon f times 1 minus pi square upon 12. Okay, so easy part is so epsilon f you can get by just first solution. Zeroth order solution is mu equal to epsilon f, and that would just correspond to throwing away this first piece. Okay, so you can see it's a power series in some quantity which is kBT upon epsilon f. Okay, and but epsilon f I haven't defined for you. But if you look at this thing, it's made up of all these constants. You can put them together. Okay, so you can show that in the process you will get expressions for epsilon f. But we will see another beautiful interpretation for epsilon f in another couple of minutes. So I am not going to define what epsilon f is. I'll define it in a slightly different way, and they will agree. Okay. So another way of saying is that epsilon f is the chemical potential at zero temperature. Kind of tautological in the sense you put t equal to 0 in my formula, and the ellipsis refers to higher powers of these quantities. And the key point here is that so there are two epsilon f has dimensions of energy, so does kBt. Okay, so now low temperature here really means kBt compared to epsilon f. It's the more natural thing instead of thinking of some combination of lambda cubed over b or something like that. Okay. So is this clear? So this is an exercise which you should do. You can even do it if you want in reverse. I mean, what I would do is write it as a plus b kBt plus c kBt square. But b would be 0 because if you see here, if you look at this as a power series, it has log z power 3 by 2, and the next term is log z power minus half. So there's a jump of a factor of 2. Because of that, I mean, you can't rule out b, but you will see that b will be 0. Okay. I'm giving you a quick argument, but okay. So please do these computations, and if I remember, I'll put it in the assignment. Okay. So now. So that will just, the problem for what is epsilon f is reduced to what is the chemical potential at t equal to 0. Okay, and we did some plots, right? We did this plot of okay, t going to 0 is beta going to infinity, right? And what was sorry, this is correct. Yeah, yeah, that's the name for it. Yes. So this is what we have, but I'm just asking for what was this function at t equal to 0. Does anybody remember, Divakar? 1 until mu and 0. At 0 temperature, this is what happens. Okay, so now so the thing is that if, and this mu is called epsilon f, this value is called epsilon f, so it's better to write it as epsilon f. Okay, this is at t equal to 0. We also plotted for other values of t, but this is the key. Okay, so now the question is, how do we fix epsilon f? Okay, okay, so we know one thing, right? So we know that n, total number of particles, is equal to 0 to infinity rho of epsilon, n of epsilon, d epsilon. Okay, so but n of epsilon at t equal to 0 is very simple. So how do I incorporate that? I just say I cut off the integral at mu or epsilon f. Okay, and what was the density of states? Semi-classical value, does anybody remember? Something epsilon power of, I don't know the constants. The, can you look up, somebody? We had worked this out a few lectures ago. By the way, there's a small correction here. We should actually put the G factor also, because if they have spin half, their G is 2. So we should put that also. I have been, in all my expressions, it's as if G is 1. So we should remember that. Okay. But anyway, so rho of epsilon would be, does anybody have that? Or I'll do that, I have to do that computation. Yeah. Repeat.
G into 2 pi b into 2n to the power 3 by 2 by h2 into epsilon.
Okay. So this is kind of simple stuff. So we can just go there and plug this in. So we can do this. So n by v, which is good, we get number density, is equal to g 2 pi g okay, epsilon power half, integral is what, 3 half, epsilon power 3 half by 3 half, so that is 2/3 epsilon f, okay, power 3 by 2. Okay, so actually there's a simpler way to understand this, which is just to say that you look at in this space, you look at the volume, it's okay, let's not worry, it's just the same computation. So this is what we get. So you can see that if you, now we can simplify things and we'll get epsilon f over 3 by 2 is equal to, this is 1 by v, so I can't compare because he writes something else. Okay, so we now we know. So this determines, so this equation, we can go back and you can rewrite this whole thing. You can see that this should be up to some, yeah. I have not missed anything, right? Okay. So this is what you get. So this, okay. So I mean, I may have, so exercises to see that this agrees with the formula from earlier, from other calculation, which is this one, right? So we said here, yeah, here when you did, okay. So, but so what exactly? I mean, this is kind of simple. So the reason, the reason you have this 1 and 0 is because everything should go to the ground state. If it were bosons, everything will go to the ground state level. But what is happening in the case of fermions, you cannot, Pauli exclusion principle works, so you have to keep filling. So you think in terms of organize it in terms of energy. So first the lowest energy will get filled, and depending on the degeneracy of spin, how many ever are there, you fill them. So if it is spin half, there will be 2p equal to 0, guys. So that's one. Then you fill the next value, so on and so forth till it gets filled, and that's the level, the value of p. We'll call it ps for Fermi momentum, the value of p at which you use up all the particles, and then you can and the relationship between pf and epsilon f is simple. It's just pf square upon 2n. Okay, so this is just nothing very very deep. Okay, but the fun part here is now not this, but to look at deviations. We want to know what is the next correction to this when t is slightly bigger. Okay, so in particular, what I want to do, I would like to compute. Okay, and there's a reason for this, and the reason is that if you look at a crystal, we had discussed that at low temperatures, the specific heat goes like there's a linear component and there is a cubic component, and we explained that the cubic component came from the phonons. Okay, so what we have to show is that gas. So if you take a metal like a alkali metal, the valence electrons, the outermost shell electrons, they actually are like an electron gas, free electron gas. They're not the ones which are tightly bound. So you have ions plus this gas. Okay, so the ionic contributions is what gives phonons. This gas of electrons is we are treating it like gas of ideal gas. And so if you compute it and if you get a linear term, we'll also get the prefactors, right? I mean, even when we did phonons, we got prefactors, etc. So same thing we will do here. So next class, that is tomorrow, we will do this computation. We'll complete it. And we have all the ingredients out here. And but because it is CV, we have to take a derivative with respect to temperature. We need the dependence on T. So we need the dependence for small values of T. Okay, so we will need mu. So in other words, I have to use the value of mu to next order, which was there. Okay, and so it's not like so when we plotted the graphs, we just said mu plot n of epsilon, and so at mu, so we wrote we just wrote, if you have some other temperature, we drew a graph like this. It goes through half or something like this. Okay, but the value of mu itself is changing. So we have to, so that has to also be taken into account. And so one can do it very precisely, but so this is what we will do next class. But right now we just done the zero temperature behavior. And we need, so for what I'm saying is that to get specific heat, we need more than that. We need at least the next term in the expansion. Okay. So, okay. So in some sense, the long picture, we started off with phonons, and then we come to this thing. So these two contributions, you put them together, and you have a very nice description of metals, alkali metals at least. Okay. So I think I'm done for today. So I'll pause for questions.